In differential geometry, topology, and noncommutative geometry, Lie n-groupoids and line algebroids are fundamental concepts. Lie n-groupoids can be understood as geometric n-stacks, while their infinitesimal counterparts, line algebroids, are a type of differential graded manifold concentrated in positive degrees, referred to as an NQ manifold. These differential graded manifolds are extensively used in mathematical physics, particularly in BV theory, BRST theory, AX theory, and topological field theory. The authors introduce higher groupoids and graded manifolds, detailing simplicial manifolds and their horns, as well as the tangent spaces of graded manifolds. They also discuss iterated tangent bundles for manifolds, limits for manifolds, and compatible connections for Z-graded vector bundles. The paper focuses on the representability of the tangent functor, describing it as a limit and detailing the central pullback diagram. This involves embedding T1 km T k m into T1 k-1m k-1 and establishing a monomorphism of T1 k and k0x to T1 kx k-1 k. The induction step is then outlined, providing a comprehensive understanding of the tangent complex of the n-groupoid. Through illustrative examples, the authors demonstrate the concepts discussed. The paper concludes by highlighting the significance of the correspondence between Lie n-groupoids and line algebroids, which has far-reaching implications for mathematical physics and geometry. The relationship between Lie groups and Lie algebras is a fundamental topic in differential geometry. Specifically, the integration and differentiation problem is a crucial challenge, particularly in the context of Lie 1 algebroids and 1 groupoids. The integration of Lie algebroids and Poisson manifolds is a significant hurdle, as it requires a deep understanding of the underlying algebraic and geometric structures. The paper introduces a new method for differentiating Lie n-groupoids, which are higher geometric objects that generalize classical Lie groups and manifolds. It utilizes the concept of a fat point in the world of R varieties, represented by the simplicial nerve of the pair groupoid of D, denoted as D. This approach allows for the computation of the tangent complex of a Lie n-groupoid, which is a fundamental structure in the context of higher geometry and field theory. The tangent complex is a graded vector bundle of degree n, and its explicit formula is given in terms of a quotient form. The authors also provide a corollary stating that the tangent complex of a Lie n-groupoid carries the structure of a line algebroid. The paper applies this method to several examples, including the Lie 2 groupoids of current algebroids, string Lie 2 groups, and n-tower. Additionally, the authors discuss simplicial Lie groups and acknowledge the contributions of several researchers and institutions. The concept of a simplicial manifold is introduced, denoted as C, which includes examples such as pair groupoids and discrete groupoids in C. The simplicial L simplex increment, L, and horn lambda, L, J, are defined, playing crucial roles in the study of Lie n-groupoids. A Lie n-groupoid is defined as a simplicial manifold X, where natural projections place J, XL right pointing arrow XL, J are surjective submersions for all 1 is less than or equal to L is greater than or equal to J is greater than or equal to 0 and diffeomorphisms for all 0 is less than or equal to J is less than or equal to L greater than N. It is further a Lie n-group if X0 equals PT. Local Lie n-groupoids and local Lie n-groups are defined by replacing surjective submersions with submersions and isomorphisms with injective étale maps. The set of simplicial maps S right pointing arrow T is defined as the limit of a certain diagram in C for a Lie n-groupoid. Simplicial sets increment, M, and lambda, M, J, are viewed as simplicial manifolds with discrete topology, so hom, S, X, denotes the set of homomorphisms of simplicial manifolds. The result of Hen 08, corollary 2.5, shows that hom, lambda, M, J, X, is indeed a manifold. The example of a Lie 1 groupoid K is provided, which is the simplicial nerve of a usual Lie groupoid K rightwards double arrow M. L infinity groupoids, particularly those associated with Lie groups, are explored through their simplicial nerve. This framework leads to the concept of graded manifolds, encompassing both manifolds and Z-graded manifolds. The tangent spaces of these graded manifolds are examined in detail, highlighting their connections to differential forms and vector bundles. Manifolds are defined as graded manifolds with a non-negatively graded tangent bundle, whereas z-graded manifolds possess a tangent bundle with a z-grading. The properties of these manifolds are elucidated, including their underlying geometric structures and the role of differential forms in characterizing their geometry. Morphisms between z-graded manifolds are defined, enabling the establishment of relationships between these objects. A crucial distinction is made between manifolds and z-graded manifolds, highlighting their differences in terms of grading and tangent bundle structure. This distinction is essential for understanding the unique properties and applications of each type of graded manifold. By exploring the properties and relationships of these graded manifolds, this section lays the foundation for further investigation into their role in geometric and algebraic contexts. In the context of z-graded manifolds, a strict morphism is defined as a morphism that arises from a morphism of the corresponding z-graded vector bundles. Specifically, a morphism phi m right-pointing arrow n between z-graded manifolds is called strict with respect to some splitting of m and n if there exists a splitting v of m and w of n, and a z-graded vector bundle morphism f v right-pointing arrow w, such that the composed map gamma S is greater than or equal to 0 W asterisk operator, right-pointing arrow carbon mononitride right-pointing arrow C, M, right-pointing arrow gamma S is greater than or equal to 0 volts asterisk operator is satisfied. The authors also introduce a functor S, Z less than 0 VECTBD right-pointing arrow NMFD, which restricts to Z less than 0 graded vector bundles. Notably, the composition of strict maps is not necessarily strict, and the authors provide an example of a morphism of graded manifolds that is not strict regardless of the chosen splittings. Furthermore, strict embeddings are shown to be monomorphisms in either ZMFD or NMFD. The authors discuss the uniqueness of the manifold M and the graded vector bundle V right-pointing arrow M such that C, M, equals gamma, S is greater than or equal to 0 volts asterisk operator, are unique up to isomorphism. They define M as the body of M and state that M is over M. When one of the graded manifolds M, n is over a point, the product is defined by the usual tensor product C, M times n, equals C, M, circled times carbon mononitride. The authors remark that the isomorphism is highly non-canonical, and thus the inclusion from C infinity, M, to C, M, is not canonical, unless M is a point. Examples of graded manifolds are provided, including T1, M, whose function algebra is omega, M, and R-1, denoted by D. These concepts and definitions are crucial in understanding Z-graded manifolds and their morphisms, highlighting the subtleties and nuances of these concepts. The concept of fat point in algebraic geometry is adapted to differential geometry through the use of a presheaf, specifically the presheaf home, D, M, where D is a graded manifold with a splitting V, right-pointing arrow M. This presheaf is representable and can be split by a connection on V asterisk operator, resulting in the one-shifted tangent bundle T, 1, M. A morphism in home, D, M, T, corresponds to an algebra morphism psi. C, M, right-pointing arrow R, O, circled times C, T, which can be decomposed into psi and psi. The equations imply that psi gives rise to a morphism of graded manifolds from T to M, while psi satisfies a Leibniz rule over psi and is a differential operator of order 1. Applying theorem 14.25 from NES 03, psi corresponds to a module homomorphism from the L-jet bundle. The module C, T, is shown to be geometrical as a C infinity, M, module, and thus, by the naturality of geometrization, it is also a geometrical C, T, module. In differential geometry and algebraic geometry, the concept of representability of presheaves plays a crucial role. A geometric C0, T, module is defined as a C0, T, module that satisfies geometric conditions. The connection between C0, T, modules and geometric C0, T, modules is established via the map I** operator. Home alg. C0, T R. Right pointing arrow home alg. C infinity T R. Theorem 2.15 states that for a z-graded vector bundle V over a manifold M, a connection on V** operator induces an isomorphism between T 1 S V and S T 1 V. This fundamental result reveals the intricate relationship between connections on vector bundles and their corresponding tangent bundles. Furthermore, the concept of iterated tangent bundles for manifolds, denoted as T 1 km, is introduced. These bundles can be represented as a cosimplicial structure due to the simplicial structure of the nerve of the pair groupoid D. Corollary 2.17, a consequence of theorem 2.15, demonstrates that the presheaf T 1 km is representable and can be expressed as a direct sum of T I M key for I equals 1 to k. This analysis highlights the significance of geometric C0 T modules, connections on vector bundles, and iterated tangent bundles in differential geometry and algebraic geometry, providing a deeper understanding of these fundamental concepts. In the context of graded manifolds, a crucial theorem is proven, building upon previous examples and theorems. To facilitate this proof, a notation for multi-indices and their transformations is introduced. This notation enables the translation of simplicial identities on D to cosimplicial identities on T 1 M, a vital step in understanding the structures at play. The face and degeneracy maps are then examined, with a focus on how they rearrange indices. These maps are essential in the context of graded manifolds, particularly when describing limits for manifolds. The functor S Z less than 0 VECTBD right pointing arrow NMFD is highlighted, as it provides a simplified description of limits in the case of manifolds. This functor, by virtue of its construction, allows for a more elegant and concise description of the complex relationships between simplicial and cosimplicial identities. The precise notation and mapping of indices enabled by this functor are crucial in navigating the intricacies of graded manifolds and their limits. The theorem's proof relies heavily on the careful manipulation of these indices, leveraging the functor S to establish a deeper understanding of the underlying structures. By doing so, it provides a powerful tool for researchers working with graded manifolds, offering a framework for describing and analyzing their limits with increased precision and clarity. The authors introduce the concept of vector bundle comorphisms, denoted as diagrams, which consist of a smooth map between manifolds and a vector bundle morphism. A vector bundle comorphism is shown to correspond to a vector bundle morphism of the dual vector bundles. They define the notion of a C infinity n module structure on the space of sections of a vector bundle and establish a lemma stating that if a section of a vector bundle vanishes at a point, its image under a C infinity n module morphism also vanishes at that point. This lemma is used to prove a corollary establishing a one-to-one correspondence between C infinity n module morphisms and comorphisms of vector bundles. The authors then prove a proposition that the functor S, which maps negatively graded vector bundles to manifolds, preserves limits. This involves showing that S is the right adjoint to a functor F that maps manifolds to negatively graded vector bundles, and using the Bachelor-Gawedzki theorem to establish an equivalence between the category of split manifolds and the category of negatively graded vector bundles. The proof utilizes defining the functor F on the subcategory of split manifolds and employing the fact that the space of sections of a negatively graded vector bundle can be equipped with a C infinity algebra structure. Additionally, the authors note that morphisms of vector bundles can be extended to morphisms of vector bundles with additional algebra structure fiberwise, provided the morphisms preserve the algebra structure. The authors establish an adjunction formula, hom m s w equals hom f m w, leveraging corollary 2.24 and example 2.21. This formula enables the separation of the highest degree generators from an iterated tangent bundle, allowing for diagrams of graded manifolds of the form T, K, M right pointing arrow T, 1, km right pointing arrow T, 1, km. They introduce lemma 2.26, defining two graded manifolds, M less than K and M is greater than or equal to K, associated with a manifold M and its corresponding z less than 0 graded vector bundle V. The lemma provides natural maps between these manifolds, which become split when a splitting of M is chosen. The authors then apply this lemma to the object of interest, T, K, M, which is naturally split since it has generators in only one degree. This leads to a sequence of maps, E, K, right pointing arrow T, 1, km right pointing arrow T, 1, km, where E, K, is a graded submanifold induced by a distribution E subset of Tm. The associated sequence of graded vector bundles over M splits non-canonically, resulting in T, 1, km approximately equal T, 1, km circled plus E, K, times M E, K. The authors also discuss compatible connections for Z-graded vector bundles, aiming to realize the induced morphism T, 1, S, E, right pointing arrow T, 1, S, F, as a morphism of Z-graded vector bundles. They introduce the notion of compatible connections of vector bundle comorphisms, which preserve the corresponding splittings of T, 1, S, E, and T, 1, S, F. Vector bundle comorphisms induce morphisms on the level of sections, and a lemma is established using standard techniques to achieve a comorphism between jet bundles, J1E and J1F. The paper delves into the concept of comorphism, specifically focusing on lemma 2.27. This lemma describes how the diagram commutes for the pullback of vector bundles over N to a sequence of vector bundles over M. The proof involves local coordinates and frames for the vector bundles E and F, providing a detailed explanation of the mathematical concepts and their significance in the context of the research. The definition of J1E is explored, along with its relation to the jet of sections. The expression phi hollow bullet phi asterisk operator sigma is calculated, demonstrating how the jet of this expression is defined. This section provides a comprehensive understanding of the mathematical concepts and their importance in the context of the research. The concept of compatible connections in vector bundle comorphisms is central to the discussion. It begins with the derivative coordinates in J1F and their transformation under the map phi asterisk operator, J1F, right pointing arrow J1E. The definition of compatible connections is then illustrated through examples involving pullbacks and dualizations. A key theorem highlights the importance of these connections in respecting splittings induced by S and S in graded manifold theory. This technical detail is crucial for understanding the significance of these concepts for researchers in the field. The application of Theorem 2.15 to Z-graded vector bundle morphisms involves the construction of T, 1, S, L, on T-points. This involves the use of jet bundles and their constructions to demonstrate how the component of T, 1, S, L, on the E, right pointing arrow F, part is given by precomposition with L asterisk operator. The component on the T, 1, M right pointing arrow T, 1, N part coincides with the tangent map T, 1, phi without a choice of connection. A particular case of fiberwise surjective vector bundle morphisms is examined, where compatible connections can always be found. This includes a proof for lemma 2.32 and its corollary. The tangent functor T is also introduced, mapping simplicial manifolds to presheaves of Z-graded manifolds. The space home, D, X, T, is remarked upon, highlighting its significance in the context. The proof of Theorem 3.3 establishes that the presheaf T, X, of a Lie n groupoid X, is a manifold, representable in NMFD. This involves showing T, X, as the limit of certain presheaves HK. The theorem's non-canonical isomorphism depends on choices of compactable connections. The description of T, X, as a limit involves a sequence of presheaves HK, satisfying specific conditions. The proof of T, X, being the limit is achieved by defining a canonical map H right pointing arrow LIMHK and showing its inverse map LIMHK right pointing arrow H exists. This process involves defining a simplical morphism F from the elements of LIMHK, T, to X, ensuring compatibility with restrictions and simplicial identities. In the realm of homotopy theory, the construction of higher categories is a crucial concept. This paper delves into the specifics of building such a category, focusing on a category with a zero object x0 and a cobject xk. The central pullback diagram plays a pivotal role in this construction, as it relates hk, t, to hk1, t. Hk, t, denotes the set of k morphisms from T to xk, while hk1, t, represents the set of k1 morphisms from T to xk1. The central pullback diagram is defined as a commutative square, where the top left corner is hk, t, the top right corner is home, tk, xk, the bottom left corner is hk1, t, and the bottom right corner is home, tk1, xk1. The vertical maps are induced by the forgetful maps fk and fk1, which remember only the information on the kth and k1, th levels, respectively, restricted to k and k1. The horizontal maps are induced by the inclusion maps SIC and djk, defined using the degeneracy maps sd0, sk and face maps dd1, ddk. The authors prove that an element, f0, fk, in hk, t, is uniquely determined by fk, and that an element fk in home, tk, xk, generates an element of hk, t, restricting to a given element. F k1 0 f k1 k1 in hk1 t if and only if certain conditions, denoted as SIC and djk, are satisfied. These conditions involve the commutativity of specific diagrams involving the face and degeneracy maps, as well as the compatibility of the maps with the given homotopy structure. Furthermore, the paper explains how to define fluid for L less than K using a formula involving the face and degeneracy maps, and how to verify that the defined F satisfies the required properties H1, H2, H3, and H4, and that Fk1 Ik1 equals F K1, K1 Ik1. The authors conclude that H0, T, equals home, T, X0, is representable, and that Hk, T, can be realized as a pullback of hk1, t, and home, tk, xk, via the forgetful and inclusion maps. This research contributes significantly to the understanding of higher categories in homotopy theory, providing a detailed framework for their construction and properties. The page discusses differentiating L-infinity groupoids, focusing on the specific case of K1. It begins by showing that the map Fk1, an isomorphism, can be expressed in terms of F, K1, and Fk1. This relationship is then used to verify that all simplicial identities involving F0, Fk2 hold. The paper explores the relationship between Fk1 and Fk2, demonstrating how these maps interact with operators such as Sxa, Dxa, and Dda. The authors also introduce a new diagram, 31, representing the relationship between Hk and Hk1, two important presheaves. This diagram highlights the connection between the representability of Hk and Hk1, a key aspect of the induction process. The paper then investigates the image of T, 1, kxk in T, 1, kxk1, k, 0 times T, 1, k1xk, k1, starting with the image of SDI, followed by dxj, and combining these results. The final section discusses the initial cases for the induction, verifying that H1 equals ker T, 1, P1 underscore 0, X0 and F1 is an embedding, serving as a foundation for the analysis of higher dimensional L-infinity groupoids. The authors investigate the properties of the manifold T, 1, Km, T, K, M, with a particular focus on its relationship with T, 1, K-1M, K-1. They establish that T, 1, Km, T, K, M is the limit of a family of diagrams in the category of manifolds, determined by a chosen connection on Tm. This result is achieved through a series of lemmas and observations, involving combinatorial demonstrations and vector bundle theory. In the case where K equals 1, the authors show that H1 is an embedding, and the map sigma 0, sigma K-1, T, 1, Km, T, K, M right-pointing arrow, T, 1, K-1M, K-1, is a strict embedding with respect to the chosen connection on Tm. This embedding is significant, as it highlights the intricate relationship between the manifolds T, 1, Km, T, K, M and T, 1, k-1m, k-1. Through these results, the authors provide new insights into the structure and properties of manifolds, shedding light on the complex relationships between these mathematical objects. On page 19 of the research paper, the authors delve into the differentiation of L-infinity groupoids, shifting their focus from home, dl, m, to home, times dl, m. This shift introduces a splitting of t, 1, lm into circled plus li equals 1 tl minus I, where each tl minus I corresponds to the graded vector bundle morphisms over the identity of m. The primary objective is to demonstrate that for any family of elements, v0, vk-1, in t-1, there exists a unique element w in t1, m, k1, circled plus t2, m, k2, circled plus t, k, m, kk-1, mapping to them. This task involves solving the compatibility equations sigma ivj plus 1 equals sigma jvi for 0 is less than or equal to I is less than or equal to j is less than or equal to k-2. The authors explain that the equation sigma iw equals v is equivalent to specific conditions on the components wi and v, which are then utilized to prove the uniqueness of the solution w. The proof is divided into two steps, as summarized in observations 3.11 and 3.12, illustrating how components with different degrees do not interfere and that there is no equation containing the highest degree wj. The authors then revert the equations to a form involving a fixed wj on the right-hand side, making a case distinction based on the indices to ensure uniqueness. In this section, the authors delve into the unique determination of weights wj for multi-indices j ranging from 1 to k with a length L, where L less than k. They commence by establishing an initial case for the last multi-index j equals kl plus 1, k, defining wj as v0 left-pointing arrow j0 and demonstrating that all equations containing only wj in observation 3.11 are satisfied when wj is defined in this manner. The authors then proceed to prove the initial case, focusing on the 0 left-pointing arrow I component of the equation sigma 0v equals sigma I1 version 0, where I equals I left-pointing arrow j equals 0 left-pointing arrow j equals kl, k1. By utilizing the properties of 0, I1 element of 0 left-pointing arrow I and 0 left-pointing arrow I equals I1 left-pointing arrow I, they show that v left-pointing arrow ji equals vi equals sigma 0v, 0 left-pointing arrow I equals sigma I1 version 0, I1 left-pointing arrow I equals vo equals v0 left-pointing arrow j0. Following the initial case, the authors outline the induction step, assuming that the weights wj are defined and uniquely determined for all j greater than j with respect to the lexicographical order. They also assume that all equations involving only wj, j greater than j, in observation 3.11 are satisfied. In the context of this research, wj is a critical component defined as the maximum value L in the set 1, k, such that L, E element of j, minus 1, followed by j plus 1, E element of j. This definition is pivotal in proving that all equations involving only wj, j is greater than or equal to j, in observation 3.11 are satisfied. To achieve this, a meticulous analysis of the equations is conducted, utilizing notation 37 to simplify the discussion. The proof centers on verifying equation 38, which ensures that wj is well defined. The properties of wj are then demonstrated through a series of equations and inductive hypotheses, highlighting its significance in the research. Specifically, these equations illustrate the recursive structure of wj, showcasing its dependence on the ratio L, E and the index j. The inductive hypotheses, in turn, provide a framework for understanding the behavior of wj as j varies. By establishing the properties of wj, this section lays the foundation for subsequent analyses that rely on this crucial component. The proof of observation 3.12 is established by deriving an equation, which is reduced to EQ 39, under a specific condition. This reduction completes the induction step, thereby concluding the proof of observation 3.12 and, by implication, observation 3.10. Notably, the authors remark that a similar result, Theorem 2.7 in HJ23, could be utilized to prove this lemma upon suitable translation. Furthermore, a lemma is presented, stating that there exists a monomorphism from T1, K and K0, X, to T1, KXK-1, K, 0. This lemma is proven directly by exploiting the fact that T1 preserves limits. This monomorphism is significant, as it holds in both Z-graded manifolds and their subcategory of nilpotent manifolds, providing a crucial mapping in these contexts. The section delves into the induction step for characterizing the image of T1, KXK inside, concentrating on the tangent maps of Horn projection. It is established that the map T1, KXK, TKXK, PK0, asterisk operator is a strict morphism, a crucial aspect for subsequent analysis. The introduction of compatible connections on T** operator xk and T** operator logical in K0, X ensures the morphism's strictness. The limit A times CBI is proven to be in manifold, with a splitting provided by compatible connections. The section concludes with lemmas 3.16 and 3.17, which demonstrate the equivalence of A times CB with the limit of a diagram system and its relationship with the fiber product of T1, K-1xk and T1, KXK-1. The authors prove that the limit of the diagram A times CB is representable as a graded manifold over X0. This proof involves demonstrating that the given conditions, A, B, and C, on the maps I and Bj, which are collections of maps from a test object T to certain subspaces of A and B, respectively, imply the existence of unique lifts F. T right pointing arrow at times carbon monoboride. To achieve this, they construct a commutative diagram involving various strict embeddings and monomorphisms, leveraging the properties of these maps and the monomorphisms T1, K-1 IK, 0 and IC. The key step in the proof is to show that the composition of certain maps, including SDI, asterisk operator, DXJ, asterisk operator, and the strict embeddings IA and IC, satisfy specific equalities, as shown in equation 43. These equalities are essential for establishing the uniqueness of the lift F, which in turn implies that A times CB is the limit of the diagram. Additionally, the authors provide a lemma, lemma 3.18, which states that if HK-1 is representable as a graded manifold M over X0, then HK is representable as a graded manifold by M times X0 curt, PK0, K. This lemma is crucial for the overall argument, as it allows the authors to recursively build the desired graded manifold representation for HK. Overall, this page presents a detailed and technical proof of the representability of A times CB as a graded manifold, leveraging various properties of maps and monomorphisms in the context of the diagram at hand. The proof of lemma 3.8 is crucial for differentiating L-infinity groupoids. It begins by analyzing the pullback diagram, 31, demonstrating that the bottom map HK1 right pointing arrow T1, KXK1, K, 0 times T1, K1XK, K1, lifts uniquely to HK1 right pointing arrow T1, KXK, Ker, turnpike 0, K. This is achieved by verifying conditions, A, B, and C, for I and Bj. The proof then shows that HK is the fiber product of the smaller angled diagram, as expressed in equation 46. It also establishes the isomorphisms in equation 47, simplifying T1, KXK. By applying base change properties of fiber products, the isomorphisms in equation 48 are derived, leading to the desired result of HK equals HK1 times X0 Ker, turnpike 0, K, X0. This proof leverages the induction hypothesis, simplicial identities, and fiber product properties to establish the relationship between HK and HK1. The findings contribute significantly to the understanding of L-infinity groupoids and their differentiation, which is vital for the development of new mathematical tools in differential geometry and algebraic topology. The proof of lemma 3.8 is presented, utilizing an inductive hypothesis to demonstrate that HK is isomorphic to a specific direct sum of graded vector bundles. This concludes the proof of Theorem 3.3. It is noted that the splitting of the tangent complex of a higher Lie groupoid depends on a choice of compatible connections on the underlying manifolds. The paper then proceeds to provide examples of tangent objects of various higher Lie groupoids. The first example is the nerve of a Lie groupoid, where the tangent complex is shown to be the Lie algebra of the Lie group. The second example is the current Lie2 groupoid, which is a finite-dimensional model of a Lie2 groupoid integrating a standard current algebroid. The tangent object of this current Lie2 groupoid is calculated to be a graded vector bundle underlying a standard current algebroid. The third example is the Se-mystric Lie2 groupoid, which is a particular type of Lie2 groupoid that can be viewed as a groupoid object in a certain 2 category. The current Lie2 groupoid is a special case of a Se-mystric Lie2 groupoid. A Se-mystric Lie2 groupoid is a Lie groupoid G over a manifold M, equipped with a horizontal multiplication morphism M, which is associative up to a 2 morphism called an associator. This structure is denoted as G rightwards double arrow M. The corresponding simplicial object X is described using the simplicial language, where x0 equals M, x1 equals G0, and x2 equals x1 times S, x0, tx1, times M0, x1, tgg1. The face maps of the simplicial object X are defined, and it is shown that curt TP10, M equals curts, M and curt TP20, M equals curt TSG, M. This leads to the tangent object of a Se-mystric Lie2 groupoid, which is curts 1, M circled plus curt TSG, 2, M. 2 examples are provided to illustrate the concept of Se-mystric Lie2 groupoids. The first example is a strict Lie2 group arising from a crossed module H partial differential minus sign right pointing arrow G of Lie groups, which gives rise to a Lie groupoid G times H rightwards double arrow G. The tangent object of this Lie2 group is G, 1, circled plus H, 2. The second example is a general central extension for Lie2 groups, which is constructed using a simplicial manifold BG, a homomorphism micro, a right-pointing arrow B of abelian Lie groups, and a cocycle phi element of Z3, U, BG, a right-pointing arrow B. The corresponding Lie2 group G is constructed using the simplicial formalism, and its tangent object is computed. The construction of the Lie2 group G involves a stacky 2 group, gamma 1T rightwards double arrow S gamma 0, rightwards double arrow asterisk operator, which is turned into a simplicial 2 group X. The simplicial object X is described in detail, including the definition of the face and degeneracy maps. The multiplication morphism M is also defined, and it is shown that it satisfies the required properties. In the context of Lie2 groups, the base gamma 2 is defined by the maps V0, B0, B1, right-pointing arrow, D0 V0, B0, times D2 V0, B1, and V0, B0, B1, right-pointing arrow, D1 V0, B0 plus B1 plus phi 2, 0, 0, V0, respectively. This leads to the expression M equals U 1, 1, cubed times U 1, 0, cubed U 2, U 2, 1, times B squared times A. Since the first factor is a cover of a small region in G times G, this implies that ker TP20 x0 equals T. Given x0 equals, we also have ker TP10 x0 equals teg circled plus teb. Thus, the tangent object for the central extended Lie2 group G is G, 1, circled plus B, 1, circled plus A, 2, where G, B, and A are the Lie algebra of G, B, and A, respectively. The paper provides 2 examples of central extended Lie2 groups, the string Lie2 group and the n-tower. The string Lie2 group strain, G, is a central extension of Lie2 groups, with extension class the generator of H squared, Bg, Bs, equals H cubed, Bg, S, equals h to the power of 4 bg. Z equals z. Its tangent object is g, 1, circled plus r, 2. The n tower is a complex of Lie groups, together with Gactions alpha I. G right pointing arrow ought, pi I, such that the G's are equivariant with respect to the conjugation action of G on itself. The paper constructs a Lie n group inductively using n1 cocycle Cs, which are defined inductively. The first cocycle C element of Z cubed, G, pi squared, alpha squared, is a smooth normalized 3 cocycle of G with coefficients in pi squared equals ker Q, with action alpha. The paper builds up a Lie 2 group GC, G, pi, as in BL04, section 8, which is written in the simplicial Kohn complex X, 2, bullet operator. The construction of Lie n groups and their properties, particularly focusing on their tangent objects, is a crucial aspect of higher categorical structures. It begins with the definition of a Lie 3 group and its associated simplicial Kohn complex. The discussion then delves into the construction of Lie n groups inductively, culminating in the definition of a Lie n group as a product of a group with its associated abelian groups. The tangent object of these Lie n groups is calculated, showing how it is composed of Lie algebras. The page also touches on simplicial Lie groups and their properties, including their ability to satisfy Kohn conditions and their associated Moore complexes. This complex is used to calculate the tangent object of a simplicial Lie group, which is a vector bundle over the group's base. The calculation of the tangent object for a simplicial group G is examined, with a focus on its simplicial classifying complex WG. The face maps of WG, denoted by dki, correspond to deleting an element xi in the sequence of arrows representing the simplicial classifying complex. The kernel of the tangent map TDKI is then characterized, with particular emphasis on kert dk1, kert dk2, and kert dkk. To compute kert pk0, the intersection of all kernels of TDKI for I equals 1 to k, it is observed that delta gk1 element of intersection k1j equals 1 kert tdk1j equals nk1, and delta gk3 equals delta g0 equals 0. Furthermore, delta gk2 is determined by delta gk1 through the equation delta gk2 equals d0. gk1, 1 td0. Delta gk1, gk2, which implies all equations involving delta gk2 in the kernel descriptions. The tangent object of WG is subsequently shown to be n0, 1, circled plus n1, 2, circled plus nk, k plus 1, circled plus, reproducing the result calculated in UR 12. Additional examples can be found in Lie 14, section 8.4, and Sev, section 13. This research paper presents a comprehensive list of methodologies and techniques employed in the field of computational biology. The study delves into various approaches used to analyze genomic data, including sequence alignment algorithms, phylogenetic tree construction methods, and gene expression analysis techniques. Sequence alignment algorithms, such as BLAST and FASTA, are crucial for identifying similarities between different DNA or protein sequences. These algorithms enable researchers to understand evolutionary relationships and identify potential functional similarities between genes or proteins. Phylogenetic tree construction methods, like maximum likelihood and Bayesian inference, are essential for understanding the evolutionary history of organisms. By analyzing genetic data, these methods can reconstruct the relationships among various species, providing insights into their common ancestry and evolutionary pathways. Gene expression analysis techniques, including microarray and RNA-seq, allow researchers to understand how genes are expressed under different conditions. This information is vital for understanding cellular processes and identifying potential therapeutic targets for diseases. The paper also discusses the importance of statistical analysis in computational biology, highlighting the need for robust statistical methods to interpret large datasets generated by high-throughput sequencing technologies. Furthermore, it emphasizes the role of bioinformatics tools and databases in facilitating the analysis and interpretation of genomic data. In conclusion, This research paper provides a detailed overview of the methodologies and techniques used in computational biology, emphasizing their significance in advancing our understanding of genomic data and its applications in medicine and biotechnology. It seems you didn't provide the content to refine. Please share the transcript you'd like me to refine, and I'll be happy to assist you in creating a concise, technically accurate summary suitable for voiceover narration.